Hello everyone. Welcome to the presentation of our paper titled Deep-Dup, an adversarial weight duplication attack framework to crash deep neural network in multi-tenant FPGA. I am Adnan Rakin and my co-author Yukui will present this work to you. In this first part of our presentation, we'll first introduce the motivation of the work and the threat model of the proposed attack implementation. Machine learning applications have been extremely popular in different applications, including but not limited to computer vision, robotics, medical applications, and speech recognition. Machine learning as a service is extremely popular in the forms of Amazon AWS AI, Google AI, Microsoft Azure ML as well. Ahmed Khwaja first proposed the multi-tenant FPGA framework where both the user and the vendor can be benefited by the improved resource utilization and low power consumption. However, such multi-tenant setup comes with potential security threats such as side channel attack and fault injection attack. Traditional machine learning attacks have followed three particular topologies. First is adversarial input attack, when a malicious attacker adds adversarial noise to the incoming data to fool the target neural network into misclassification. In the second class, the adversarial weight perturbation, which is our goal in this work, looks to modify the weight parameters within the neural network to hijack the output into a wrong class. In the third topology, that is the backdoor or Trojan attack, looks to modify both the weight parameters and input trigger to misclassify the target neural network. As stated already, our domain of attack would be adversarial weight perturbation, where we look to modify the parameters within the neural network to cause misclassification at the output. Objective of the work is to compromise the performance of the machine learning model, for example, degrading the test accuracy of deep neural network. The application of the work mainly focuses on multi-tenant cloud FPGA server.
In this slide, I will introduce the hardware threat model in multi-tenant FPGA. As we can see in this figure, tenant A and tenant B are coincide on one FPGA chip. All tenants have flexibility to program their applications, such that tenant A gives us a malicious circuit, and tenant B provides a DNN accelerator. Around this FPGA, we can see some certain hardware resources are shared by tenants, such as external I/O and FPGA core power supply. One thing we need to mention is, in order to enhance the clock integrity, the clock management tail are powered by specific supply voltage resources, which is isolated from the core power supply. Next, we discuss our attack topology, which consists of two key components. The first one is a hardware fault injection attack scheme. The second one is an algorithm to search vulnerable weight index, where we can apply our hardware attack efficiently. Finally, we demonstrate how to combine those two components to produce an end-to-end attack framework. Our proposed hardware attack focuses on DNN accelerator on multi-tenant FPGA. As we all know, DNN applications are data-intensive. Thus, it requires a simple but high-performance communication protocol, such as Amber AXI4, to exchange massive data between hosts and accelerators. The schematic of the FPGA-based DNN accelerator is illustrated in this figure, which constructed by three components. The first one is the processing system. The second one is the processing engine. The third one is the external memory. Particularly, DNN computation is usually accomplished into a layer-by-layer style. For example, input data like images and DNN model parameters of different layers are usually loaded and processed separately. If the injected fault appears while the data transmission from the external memory to the FPGA on-chip buffer, the accelerator may utilize those incorrect weight to infer the images. It will achieve a decrease in the overall inference accuracy. FPGA utilize a hierarchical power distribution system, which consists of some power regulators providing different supply voltages. A critical component for power distribution system is the capacitor Cout, which has been utilized as the power bank to supply the FPGA dynamic power. Formally, in the equation, delta I and V represent the change of the output current and the voltages of the power supply. F switch denote the regulator switching frequency. The default output capacitance of the FPGA is usually set to compensate for the current difference for at least 2 clock cycles with a tolerant voltage drop. This figure illustrates our power-plundering circuit to tackle the proposed attack. In order to bypass the delay checking rule, we modify the ring oscillator with a latch to break the combinational loop. In this figure, we analyze the data transmission process of the AmberX4 data reading channel. Assume the data has been packaged into DI and transmitted from the external memory to on-chip buffer. The normal situation shows in the left side, and in the right side, we apply a voltage glitch during the D2 data transmission process. As a result, the D2 is partially sampled twice by the receiver clock, which injecting fault to the received data package. Well, we have knowledge of the malicious circuit and attacking principle. The problem for now is the attacker should know when to tackle the attack. Time-to-digit converter is a good choice to trace the behavior of the target DNN application. After getting the tracing waveform, the attacker can proceed a targeting strategy. This strategy is buffered on a BRAM, waiting for the starting point of the future image inference loop to place the attack automatically.
Having developed this new attack surface, adversarial weight duplication attack, we ask ourselves two key questions. First, how successful our attack is in injecting the fault. The answer is the fault injection success rate is about 58.91%. However, the next question we should ask is, with this success rate, how successful a random AWD attack will be in depleting the DNN performance. For example, we attack a VGG11 model on C410 dataset. Clearly, the blue curve shows a random AWD attack fails to degrade the test accuracy of a neural network. Hence, we need a better algorithm to search for vulnerable weights. Based on the results that I presented in the previous slide, two questions became clear. How to use AWD attack efficiently? Can we improve random AWD attack? On top of that, we put a challenge on ourselves is, can we conduct a black box attack without any information of the target machine learning model, for example, weights, gradients, and architecture? The obvious solution to search for this vulnerable weight would be an evolutionary search algorithm. In this work, we propose progressive differential evolution search, PDAS. The proposed PDAS algorithm starts by initializing some random weight index W1, W2, and WZ. At that random weight index, we'll perform AWD attack one at a time and evaluate a fitness function. By fitness function in this work, we mean is the neural network loss function. The objective of the algorithm is to maximize the neural network loss function. As a typical evolutionary algorithm, the next step is to perform mutation. The job of mutation is to propose new candidates who has a better fitness function than the previous candidates. In this work, we used 4 mutation strategies. Among them, a sample mutation strategy can be as follows, where we generate 3 random numbers A, B, C. Using those random numbers, we choose 3 different weights to produce a new candidate weight index. This new weight index can be within a various range. The next step, which is the crossover step, which ensures the new weight index generated is in a valid range of a neural network. After the mutant index has been generated, the next step is whether to select it or skip it for the next iteration. The decision depends on the value of the fitness function. If the fitness function is higher than the existing population, that mutant index will be kept within the population for the next iteration. Otherwise, we'll just simply skip. This process is repeated for Z evolution. After Z evolution, the AWD attack will be performed at the winner index. By winner index, we mean the highest fitness function within the surviving population. We combine both the hardware fault injection technique and software search algorithm in a white box framework first. In a white box framework, the attacker knows the architecture, weights, and other parameters. The key advantage of the white box framework is that the PDS algorithm can be performed offline, where the attacker generates the sequence of weight to be attacked in an offline target model and proposes to the target triggering algorithm. After the faults being injected, then the attacker can always check whether the attack is being successful or not. If not, he can always go back and generate a new set of indexes and repeat the attack. In a black box setting, the attacker doesn't have the offline replica model. Instead, what he will do is propose some mutant index to the triggering algorithm and evaluate the fitness function by attacking the deployed FPGA directly at that winner index. After evaluating the fitness function, the attacker will restore the weight back and continue this process for Z evolution. After Z evolution, the attacker will finally perform the attack at the winner index for the current iteration. The attack will continue for repeated iteration until it gets success. In this final part of the presentation, we'll present our experimental results and summary of our work. To evaluate our attack, we use different kinds of datasets and DNN architectures. We also use the FPGA prototype from Xiaolin with the following frequency set. Here is a demonstration of our attack where after AWD attack, the weights becomes duplicated, and after performing the weight duplication, the yellow V2 model can no longer recognize the person class, which the previous clean model used to perfectly recognize the person class. We also performed the attack on the whole dataset, where the initial mean average precision was 0.428. After 63 rounds of attack, the post-attack mean average precision went down to 0.14. Our attack has achieved tremendous success across a wide range of deep learning architectures. In particular, compact architectures like MobileNet V2 have been found to be extremely vulnerable, which requires just one round of attack to fool the neural network. Previous work have also found compact architecture like MobileNet V2 extremely vulnerable. Also, we can attack a certain class of ImageNet dataset. For example, attacking ostrich class, Deep-Dup can misclassify all the images within the ostrich class. To summarize, we propose a novel attack surface on multi-tenant FPGA. Also, we propose a novel algorithm to locate vulnerable weight index in deep neural network. By combining this novel attack surface and algorithm, our end-to-end Deep-Dup attack framework can conduct black box attack as well. We successfully demonstrate that Deep-Dup can completely deplete the DNN performance close to a random guess. Thank you everyone. Feel free to ask any question or reach out to any of the authors if you have any specific question about the work. Thank you very much.